it's reasonable to understand why VMware did this. They were probably trying to reuse their real mode emulation code for if you wanted a DOS guest or something like that. It's obviously pretty reasonable to use supervisor access for that because it makes no difference. But in virtual 886 mode, Intel actually guarantees that you're always running as Ring0. It's as a CPL3. It's very clear in all of the manuals that this is guaranteed. So this was an error. And surprisingly, we were able to exploit this, get Ring0 code execution in a VMware guest. The reason we were able to do this was because the Linux kernel has a magic check, has a check for a magic CS value to look for an unusual event caused by PNP BIOS support. But because this magic value was something that you wouldn't normally be able to set, in virtual 86 mode, you must be allowed to set it because this is how real mode addressing works. Obviously, addresses are 16 bits in real mode, but the address space is 20 bits. So you do this by shifting around CS and adding it to IP. So in order to access the full 20-bit address space, you need to be able to set any CS value. Obviously, this has a special meaning in protected mode, but in real mode, yeah, it doesn't mean anything. It's just part of the address calculation. To form a physical address from an address. So, believe it or not, we can actually exploit this error. It might be surprising, but we worked on this and we actually got it to work. So all we have to do is mmap our shellcode at null, and then we enter VM86 mode. So as when we were working on this, there was a new feature that was beginning to gain popularity called mmap main addr. At the moment, it's quite well known and well used, but at the time, we were concerned that maybe people would say this issue wasn't really realistic because of mmap main addr had just been introduced. So we found a way to bypass that as well that we're going to talk about later. All we had to do was set up a far call to a non-present page at SS when a non-present page was the SSSP address. A PF is delivered, which is as expected. But because we can set these magic values in CS, and then which is recognized as a PNP BIOS fault, then because the kernel wasn't expecting this fault and there was no handler set up, the fault handler isn't installed. It's a BSS object, so it's set to null, and the kernel just jumps to null, and then you've rooted the machine. So this is how we triggered it. We basically you set some nonsense in ESP and SS so that you'll cause a page fault because obviously this page isn't going to be present. Then we set CS to 90, which is the magic value for PNP BIOS faults. And then we did this far call, and that was it. Basically, the kernel would just jump to our code as at Ring0. So this was one of the first issues we found with page faults, but we found some more as well on Windows. So obviously, it's well known that if the kernel ever trusts any data from user space, then there's going to be a security issue somewhere. But it's not just the presence of data that users control, it's also the presence or absence of data. So you can set up some nonsense and tell the kernel this is like some data structure is expecting, or you can say there's more data here than was expected, or less data than expected, and strange things can happen. So by claiming we have more data available than we really do, then we can reach lots of unusual error paths. This is mainly true on Windows. Because the main system types are large interdependent structures that often have multiple components, and they sometimes have version numbers where you have to read the version number first to see how big the structure is going to be, and then they can have variable sized arrays. This isn't really the case on Linux, where at best you have one structure that can be read in a single operation, or at most two operations for things like sized for something like, I don't know, write V structures. IO vectors. But on Windows, yeah, reading data from user space can be a complex operation. And we found an example of this that could result in a privilege escalation on every version of Windows NT. The bug wasn't particularly exciting because you had to win a race condition to win it, to get code execution. So it wasn't particularly exciting for attackers simply because 9 times out of 10 you're going to get a bug check rather than code execution. But it was a legitimate issue, and it was a double free in NT FilterToken. So NT FilterToken is the backend system surface that makes the Win32 API create restricted token work. How NT FilterToken works would be that you'd pass it would pass a pointer to a helper routine that would try to capture all this complex SID data that it needed to pass. But we can force this to fail. But we can make a check pass that says the data is present because by putting by starting the structure on a present page, and then saying it spans across a page boundary to a no access page. So we can cause some unusual error conditions like this, and by making this structure straddle a page boundary. So on error, this helper routine that was supposed to capture this user data would release this buffer that it was going to save the data into. And then return to NT FilterToken, but NT FilterToken didn't handle this correctly, and it would try to free the buffer again. So because there's only a short period between these two events, the kernel detects a double free and bug checks. So you only get one attempt to exploit this, and you need to get that buffer reallocated somewhere else within this very short period. So we know this is exploitable on MP systems because using a debugger we can let ourselves win the race condition every time. But in reality, nobody's going to be, no real attackers are going to be interested in this bug simply because they'd only win 1 in 100 times. It was possible and it was a fun bug, and there's a URL for some example code that you can check if you're interested in how I did this. Okay, so this is another vulnerability in Windows NT. So this is a quote from Rusinovich in Windows Internal 4th edition. He explains that moving GDI from user mode to kernel mode has provided improved performance without any significant decrease in system stability or reliability. I think you might regret this quote. Maybe it's true, but there's no question that GDI represents a significant kernel attack surface now. And it's possibly the most easily accessible remotely. So it's obvious to us that the font passing was going to be one of the weak points, simply because it's so easy to access via Internet Explorer's app font face support for CSS, which allows arbitrary web fonts to be downloaded for your web pages. This was probably our most critical discovery over the year that we were working on this, simply because just by visiting a website you could execute arbitrary Ring0 code. This is interesting because it doesn't matter whether you're sandboxed or you're unprivileged or using protected mode. It makes no difference. We can exploit that and become the most privileged user on the system. It doesn't matter if you don't have administrative access or anything like that. It was easy to escape. So the way this worked was that the font format supported by Internet Explorer is called EOT, which is Embedded OpenType. It's essentially just a trivial DRM layer added on top of TTF format fonts. It defines some interesting data compression subformats called CTF and MTX. We actually also pwned these as well with some Ring3 vulnerabilities. These are, you can see MS10 001, but there's a couple of others. I don't remember the numbers. But EOT, is basically just added compression and reduced redundancy. CTF and MTX are actually quite clever data compression formats, and they're quite interesting to read. They do some cool tricks to make fonts as small as possible. I believe Microsoft licensed this technology from AGFA, and they published some documents on it. They're actually pretty cool if you're interested in data compression. Sorry. So, EOT adds some pretty silly extensions, things like support for XOR encryption and some other DRM techniques. The XOR encryption is really silly. It basically just, if the flag is set that says this is encrypted, it basically just XORs the entire data stream with the fixed byte 0x50. So, yeah, it's not particularly challenging to decrypt that. There's also some other another DRM technique called root strings. I think the idea is that if you have a font that you've licensed and you only want it to be accessible on your website, you'd put your website into you put all the URLs that you want this font to be accessible for into the EOT file, and then sign it. But the signature is ridiculous. It's basically just add all the character values and then XOR it with a fixed 32-bit D word. So yeah, it's not particularly challenging to defeat this. So yeah, this is all handled by a library called T2 embed. But basically, it just takes the EOT file, handles all the XOR decryption and so on, and then passes it to GDI. And then everything from that point on happens at Ring0. So this is pretty scary. And it turns out we were able to find lots of integer errors when GDI passes the TTF directories. So the directories are basically at the start of a TTF file, and they explain where each table is in the rest of the file. This code was all executed at Ring0, and the code was really old. It was unchanged since at least NT4. And in fact, if you go to ftp.microsoft.com, you can still download NT 3.1 service packs, and you can see kernels as old as like 94, 95. And the code is very similar. It's barely changed. So Microsoft wasn't alone. There were lots of other implementations that we tested that were vulnerable to pretty much the same bug. But it was mainly serious on Microsoft platforms simply because they ran this code at such a high privilege level. So this was obviously exploitable remotely, but we only worked on a local exploit just for demonstration purposes. It was a very reliable and nice to exploit bug. Yeah, so this one was pretty fun.
We'll talk a bit about null pointer dereferences. So in general, what we call null pointer dereferences aren't necessarily null pointer dereferences. It's just in general two userland pointer dereferences, just when the kernel dereference is a pointer that goes to userland. And of course, if at any time the kernel trusts data in user space, there is a likely privilege escalation. So of course, the reason why most people call this null pointer dereferences is because null is a very common value. Because since it's a common initialization value for pointer, it's also a common error code returned as a pointer. And it's a special value in C. And so some people just expect it to be special to the underlying hardware, but it's absolutely not the case on x86. And very interestingly, they used to not be exploitable. So if you were familiar with Linux 2.0 and the versions before that, actually segmentation was used, and the kernel had its code base and its data segment base both above page offset, so basically above all userland data in code. So a different pointer without a segment override would never reach userland, which was quite convenient because I mean you explicitly had to write a segment override when you wanted to reach userland, so you couldn't unexpectedly reach userland, which was a cool feature. So wrong pointer dereferences didn't become to userland pointer dereferences automatically, and so their destination would be harder to control. Of course, you can argue that you still have some control over the kernel's address space from userland. So first, because there is this usually this hyperspace inside the kernel space that maps the physical memory, and also because, of course, indirectly you control some kernel structures, but still it would be way harder to control and to exploit those bugs in this situation. And interestingly, I remember that in 2004, 2005, we had some interesting threads with Linux kernel developers who did not understand the security consequences of them. And it was not really clear if they just expected null to be special to the underlying hardware, or if they still remember the more early days of Linux when this was not exploitable, but it was exploitable on other platforms. So I don't know what happened, but for some reason a lot of people didn't think this was an issue. And it was very surprising because it was one of the most trivial and easy to understand issues, but many people didn't get it. And so even recently, a few even senior kernel developers in Linux didn't understand that. We'll talk about mmap minadre later, because now this problem, I think, is very widely understood, and there is even a feature in the Linux kernel to try and prevent you to exploit this. So we found of course a couple of those types of bugs. One of those was the Linux kernel sock10 page bug we found last August. It's quite well known, and actually it was nominated for a Pony Award yesterday because it affected all Linux kernels from 2.4 revisions and 2.6 revisions to date. So it was 10 years worth of Linux kernels, and every major distribution shipped vulnerable kernels. It was a null function pointer dereference, which makes it even easier to exploit. It was very, very, very easy to exploit. And we've seen public exploits for like a lot of architectures. So the way it works is The reason for this is every socket in